Day 1, approximating areas. All right, let's say we have a function. It's a relatively nice function. In other words, it's continuous and doesn't do anything very strange. And then we have a value a and b that form an interval on the x-axis and a vertical line at a and a vertical line at b. And let's say that we want to find the area under the curve. And so when we say under the curve, we mean between the x-axis and the function. How would you do this? If the function's particularly nice, like if the function is, say, a linear function, you can just use some basic geometry to calculate the area. You know, if it's a horizontal function, then you would just have a rectangle, and so the area would just be the rectangle formula. But that gives us an idea, actually. So this is not a linear function that I've drawn. This is some kind of curve. But if all we want to do is approximate this, we could divide this region up into a bunch of rectangles, and then use the area formula for rectangles, which is just width times height, and add that up, and that will at least give us an approximation. So to represent that, first of all, we need to take this interval AB and partition it into subintervals. And let's say that we want to do this in 4 intervals. So if we want to do it equally, then the length of each subinterval would be b minus a over 4. There's nothing special about 4, I just wanted to choose a particular value. So b minus a over 4, okay. That's going to be like delta x, okay. All right, and then we're going to do some more notation here. So I'm going to call a x sub 0, and then we want 4 rectangles, right? So this will be x1, x2, x3, and b is x4, as you would hope, okay? And let's draw our rectangles, but how tall are they going to be? All right, so we have to make a decision about how we're going to uniformly determine our rectangle heights. Not uniformly, I don't mean that they're all the same height, I just mean we need some procedure, okay? So the procedure I'm going to use right now is I'm going to choose the left endpoint of each subinterval. So, let me be more specific. I'm going to choose the left endpoint of each subinterval, and then I'm going to plug that into the function, and that'll give me the height of my rectangle. So my first rectangle is going to have height f of a, or f of x sub 0, and so it's going to look like that. So it's undershooting the function value. It's an underestimate, right? Let me write that down. So this first rectangle is height f of x sub 0, or f of a, times what? Well, it's b minus a over 4 is the width. Or to make that a little bit easier, we can just write that as delta x. Or delta x is b minus a over 4. And then my second rectangle, its height is going to be determined by the function value at x1, x sub 1, which is right here. And that's going to be kind of a little bit of an overshoot of the function. Okay? So this one is f of x1 times delta x. And then the next one is going to be the function value here at x2. And then the next one will be the function value at x3. So it kind of looks like in one of our rectangles we overshot, and the other three we undershot, and the other three we overshot the function. And so adding all that up, we would have, let's kind of write the whole sum out because we need to add these areas. We would have f of x sub 0 times delta x plus f of x sub 1 times delta x plus f of x sub 2 times delta x plus f of x sub 3 delta x plus f of x sub 4 delta x. So this big sum is our area approximation. And I'm going to call this a left area approximation. And you can probably imagine, sorry about my miserable handwriting, but you can probably imagine that we could also have a right area approximation by taking the, oh, you know what? I have an error here.